In this lesson, we're going to learn how to work with problems involving related rates. Now, related rates are looking at how two different derivatives change with respect to a third variable. Often we will use time in most of our examples. So, for instance, consider the vase that you see below. Now, suppose we're going to fill this up with water, and the water is going to come out of a spigot or a faucet at the same rate. It's going to come out at a constant rate. Now, at the different points, the rate at which the height of the water is going to be increasing at different speeds. So, for instance, if the water is pouring in from the top here, and it's coming in at a constant rate. Let's say its rate is always, this would be a volume, so let's say the rate of change of the volume is dV dt is 5 cubic inches per minute. I don't know if that's a reasonable amount, but just making something up here. It's a constant rate though, so it's always going to be flowing into the vase at 5 cubic inches per minute. Now, at point A, this water level right here is going to take a little bit of additional time to fill. Let's say we want to fill a 1-inch slab of water. Okay, so I'll just kind of draw in a 1-inch slab of water. So that top slab of water is going to take a certain amount of time to fill up. If we look at point B, the amount of time it's going to take to fill up a 1-inch slab of water here is going to be a lot less time, because the amount of volume required to fill that inch is much less than at point A. So the rate at which the height of the water is increasing changes with respect to the shape of the bottle, even though the rate at which it's entering the bottle is the same. So this is how we are considering rates of change compared to one another with respect to a different variable. Let's try some actual example problems with real numbers, and hopefully this will make a little bit more sense. Starting with a pebble is tossed into a pond, which produces waves of concentric circles. The radius of the outermost wave is increasing at a rate of 1.5 feet per second. When the radius of the outer wave is 6 feet, at what rate is the total area of the disturbed water changing? Okay, so here is the situation. So we have this pebble that's thrown into a pond, and it lands at a point. Now, as it, here's our pond. Okay, and as time passes, we have waves that are going to extend out from this point where the pebble went into the water. So that's where we're getting these concentric circles. Okay, so these are just waves that are moving outward from that center point. Now, we're told that the radius of the outermost wave is increasing at a rate of 1.5 feet per second. So let's say that from here to here is a distance r. So the rate of time that that radius changes, that's a derivative. So we write it as dr dt. And this is known as the rate of change of the radius with respect to time. And that's always how we interpret derivatives. It's a rate of change of some variable with respect to another variable. So in this case, we're looking at the rate of change of the radius of the outermost ripple, or the outermost wave, with respect to time. So the rate of this radius, we are told, is changing, and it's increasing at a rate of 1.5 feet per second. So this is 1.5 feet per second. Okay, so in 1 second, the outermost wave is 1.5 feet from the center point. In 2 seconds, the outermost wave is 3 feet away from the center point. In 3 seconds, it's 4.5 feet away from the center point. So every second that passes adds another 1.5 feet to the radius. Now, what we want to know is when that radius reaches 6 feet, what rate of change is the total area of the disturbed water? So we want to look and see how is the rate of change with respect to area compared to the rate of change of the radius. So we need an equation that relates area and the radius. All right, and the equation that relates those two together is the area of a circle is pi times r squared. This is comparing area and the actual radius of the circle, but it's not comparing the rate of change of either one of those. So we need to differentiate this. In order to differentiate this, we have to use the process of implicit differentiation with respect to a third variable. So we have our equation. Now we're going to get our derivative with respect, to time. And time is not a variable that exists in this equation, so we have to kind of introduce it. All right, now I'm going to differentiate the variable a with respect to time. So I go ahead and differentiate as I would normally. That's just 1. Whenever you take the derivative of a linear variable, it's multiplying constant, which is 1 in this case. But you multiply by the derivative of the inside part, which would be the derivative of a with respect to time. On the other side of this equation, I need to differentiate the radius with respect to time. So r squared, I just treat it as an outer function, and the derivative of r squared would be 2r. So I'm going to have pi times 2r, but then I have to also multiply by the derivative of the inside portion, which is dr dt. So my related rate formula is dA dt is equal to 2 pi r dr dt. There are two different derivatives in this problem, and I can't stress enough how important that is, because if you're relating rates, you have to have at least two derivatives, because derivatives measure rates of change. It's very easy to say the derivative of that equation is 2 pi r, because you differentiate with respect to the radius. But that's not telling you how the rate of changes compare over time. You have to have two separate derivatives at least to have a related rates formula. Okay? Now, with that, these problems generally solve themselves at this point. There's just a couple of things to plug in. So let's go back to our problem and see what kind of given information we have and what we need to find out. All right, so first off, we have that the rate of change of the outermost wave is increasing at a rate of 1.5 feet per second. So we have that to plug in. We want to know when the radius of the outer wave is 6 feet, what's the rate of change of the disturbed water, the total area of the disturbed water. So we have, I'll just write it down here so that we don't have to keep scrolling up and down. All right, we have the rate of change of the outermost wave with respect to time is 1.5 feet per second. And we want to know when the radius is equal to 6 feet, what is the rate of change of the area? And since it's asking for a rate of change of the area, look at the way the question is stated. At what rate is the total area changing? So you're looking for a rate of change, which is you're looking for a derivative. So when the radius is 6 feet, what is dA dt? Let's plug everything into our related rate formula. So dA dt is what we're looking for, so I'll leave that alone. That is equal to 2 pi times our current radius times the rate of change of our radius. And a lot of times, if you have a decimal already in the problem, your final answer is fine to approximate with a decimal. I'll go ahead and do that here. So getting out the calculator, 2 times 6 times 1.5, that's 18. So we can say that it's actually 18 pi. But then approximate that with, so take 18 times the value of pi. So 56.5, I'll just take it to one decimal. So approximately 56.5. The units on here just follow the units of measure that were given previously in the problem. So this is an area, and area is measured in square units. So this would be square feet per second. Next, air is being pumped into a spherical balloon at a rate of 6.5 cubic feet per minute. Find the rate of change of the radius when the diameter is 1.75 feet. All right, so we have this balloon that's spherical, and I know that balloons aren't really spherical, but for simplicity's sake, this is a spherical balloon. All right, because it's spherical, that means there is a center point, and that center point defines a radius for us. So from the center to any point that exists on the sphere is r. Now, we have what information given to us. Let's take a look. So air is being pumped into a spherical balloon at a rate of 6.5 cubic feet per minute. So cubic feet. That's a hint that this is volume, because volume is a measure of something cubed, area is a measure of something squared, and if it's linear, then that's not going to be, it's just going to be along a line. So anyhow, this is cubic feet, so it's telling us a volume. So the rate of change of the volume, so dV dt, is equal to 6.5 cubic feet per minute. So cubic feet per minute. All right, so that's that first piece of information that's given to us. They want us to find the rate of change of the radius. Okay, so the rate of change of the radius would be dr dt when the diameter is 1.75 feet. So the diameter is the distance all the way across. So like from this point here all the way across. The diameter of this sphere is 1.75 feet, which means the radius is half of that. So we're looking at the rate of change of the radius. We need to make sure we take this measurement in terms of the radius. So instead of saying when the diameter is 1.75 feet, we're going to say when the radius is 1.75 divided by 2. And I'll just make sure to get that accurate, so I'll use the calculator here. So 0.875 0.875 feet. Okay. In order to solve this, we need a formula that tells us how the variables volume of a sphere and radius are related to one another. All right, so volume and radius is V equals 4/3 pi r cubed. All right, so that's the volume of a sphere. Now, I need to come up with a related rates formula. So changing this into a related rates formula, so I'm going to take the derivative of both sides of this with respect to time. So it will be dv dt. 4/3 and pi are both constants, so we kind of leave those out of the calculation and just say 4/3 pi. We take the derivative of r, which would be 3r squared, times the derivative of the inside part, finishing off that chain rule. So my related rates formula in this case is dv dt. The 3's are going to cancel, so it's just going to be 4 pi r squared dr dt. Let me make that look more like an r. There, looked too much like a little v. Okay, so we have our information. We're ready to plug in and solve this problem. I can't stress enough, however, when you get this derivative, you must have two separate differentials inside the problem. If you don't, you need to go back and get the derivative properly, because in order to relate two derivatives with respect to one another, you have to have two derivatives in the problem. If you only have a dv dt, you're not going to get the right answer in the end. Okay, so what we were given in the beginning is that dv dt was a constant 6.5 cubic feet per minute. So I'm going to replace that in, say 6.5 for dv dt. That's supposed to be equal to 4 pi times the square of our radius. And they asked us to find dr dt when the radius was 0.875 feet. So I need to plug in 0.875 in for my radius. Then that's going to get squared. And over here is my remaining derivative, dr dt, that I want to solve for. I think I'm just going to go right into an approximation here. There's plenty of decimals floating around. So let's see. 4 pi times 0.875 squared. That's everything on this one side of the equation. Okay. Right, that's that value. Now I'm going to divide this number to the other side of the equation. So it's going to be 6.5 divided by, and I'm going to hit second and answer. And that's a great way to make sure I don't have to copy all the decimal values from the previous result. The calculator will do that for me. So dividing, I end up with 0.68 is my dr dt. So that's the rate of change of the radius. Our original variables were cubic feet per minute. So time is still measured in minutes, but the length is just measured in feet in this case. So this is going to be 0.68 feet, well, don't have enough space to write that, feet per minute. And that is my dr dt. Jack sits atop a giant magic beanstalk located 350 feet from his house that's rising at a constant rate of 200 feet per minute. At what rate is the distance between Jack and his house changing when the beanstalk is 600 feet tall? Alright, so we have the beanstalk, which I'll just draw like this, and then we have Jack at the top of the beanstalk, and we have Jack's house over here. And the distance between the beanstalk and the house, I'll just use this point as a reference, is going to be 350 feet. And that is a constant distance. So the beanstalk's never going to get any closer. It's growing straight up at a right angle to the ground. So we're not going to worry about it getting any closer to the house for any particular reason. Now, the beanstalk is changing. It's increasing. It's getting taller at a constant rate of 200 feet per minute. So let's put in some variables. So this is like an x distance, because it's horizontal distance between Jack and the house. And what's nice is that is constant. Now, this distance here would be the variable y, and that's a vertical distance, so that's why I'm using y right now. That's the total height of the beanstalk at any point in time. And I'm going to use this as a point of reference, but of course it's the same height as the other side of this beanstalk here. Okay, so what we're told then is that the beanstalk's rate of change, so dy dt, is 200 feet per minute. Okay, that's an important piece of given information. What we want to know is at what rate is the distance between Jack and his house changing when the beanstalk is 600 feet tall. So, distance. So this point right here is what I will say is the location of Jack. That's the distance between Jack and his house. Okay. That distance is going to be measured using the quadratic formula. So what we can say is this distance between Jack and his house is the square root of whatever the current y value is squared plus the square of that x value. And that's going to give me a formula for the distance between Jack and his house. And we want to know the rate of change of the distance with respect to the height change in the beanstalk. Now, one problem we're going to run into, it makes sense to call distance d, right? We're going to do a derivative of that. So it's going to be like dd dt. So let's change that. Instead of calling it d, let's call it s. So s is the distance between Jack and his house. that will make it ds dt in the end, and that will make a little bit more sense. Now the beanstalk is at a right angle, and that's good because we're assuming it's at a right angle at least. And that's good because we can use the Pythagorean theorem at that point. So let's take a look at how we can get started in this and start plugging in information and going from there. So keeping in mind what I want to find out, the question is asking me, at what rate is the distance between Jack and his house changing? So we want to know what is ds dt, so that's the rate at which the distance between Jack and his house is changing, when the beanstalk is 600 feet tall. So when y is equal to 600. So we have this formula that relates s and y, but we need to change it into a related rate formula. Okay, so it's relating the variables s and y. It's not relating the rates of change of the variables s and y. So that's why we can't just use the formula as is. So we need to come up with a related rates formula. Whoops. Now, in order to do this, I'm going to make things a little bit simpler for us and call this formula, I'm going to change it just a bit. I'm going to say it's s squared equals y squared plus 350 squared. Let me find out what that is. 122,500. That's the formula that I'm going to use here. Now, when I get a related rates formula, I would be taking the derivative of that formula with respect to t on both sides. Okay. And because I'm doing implicit differentiation, it doesn't matter that I write the equation implicitly, so I got the s squared written by itself instead of an explicit equation where s is by itself. And that actually saves me a lot of effort because making it s squared is equal to y squared plus 12, 122,500. That is only going to require the power rule when we go to get the derivative. If I left it with that square root, we were going to have to use the chain rule. So that's actually a nice improvement. All right, so the derivative with respect to t of s squared is going to be 2s times ds dt. So it's the derivative of the function itself times the derivative of the inside part, ds dt. Over here, a similar thing happens. I'm going to have 2y, because the derivative of y squared plus 122,500, that number is a constant. It goes to 0. So the derivative is just 2y, but then we multiply by dy dt, the derivative of the inside part. Now at this point, it doesn't make a whole lot of difference which of these you solve this for. The question is asking for us to solve for ds dt, so I'm going to get ds dt by itself. And I'm going to divide 2s from both sides, leaving us with ds dt. The 2's cancel here, so y over s dy dt. And that's our related rates formula. And that's not bad. What we need to know is dy dt, so the rate of change of the beanstalk with respect to time. We were given that originally as 200 feet per second. And we need to know how tall the beanstalk is. That was given. We want to know when this is occurring, when the beanstalk is 600 feet. We also need to know what the distance between Jack and the house is at that particular point in time as well. So we have to find out what is S when Y is equal to 600. And there we can just go to the original formula that we wrote. So S is the square root of, in this case, 600 squared plus 350 squared. And that's not going to be a nice round number, I'm certain of it. So let's just see what it will be. So that's the square of it. If I take the square root, we've got, I'm going to approximate it to 695. So we'll say this is about 695 feet. So when the beanstalk is 600 feet tall, Jack is about 695 feet from his house. Okay, so then the rate of change of the distance between Jack and his house is going to be ds dt, and I'll say that's approximately because we approximated with the 695. So it's approximately 600 over 695, and that's multiplied by 200. So that gives me an answer of, take 600 divided by 695 times 200. So about 173 feet per minute. So he's changing at about 173 feet per minute at that particular instance in time. Now, if you wanted to get a more accurate answer, one thing that you could have done is this. So when you get that measurement between Jack and his house when the height is 600 feet, so that was the square root of 482,500, you can call up that previous answer and say this would be 600 divided by the previous answer. Even if you wrote 695 down, you can still use all the decimals that are available to you. Then multiply that by 200, and it might just give you a slightly more accurate answer. It might round to something slightly different. In this case, it did not. So sometimes when you're working homework problems, you'll find that the answer is extremely close but not exactly right. And oftentimes, if you're doing the procedure right, it could just be due to rounding error by rounding off answers throughout the problem. The best idea is try not to round anything off until the very end, and that will help ensure you get the most accurate answer that you can in the end. Wood mulch is removed from a train car and placed on a conveyor belt that transports the mulch and drops it into a conical pile for further processing. The mulch falls from the conveyor at a constant rate of 7.5 cubic meters per minute if the height of the pile is 4 meters and is changing at a rate of 0.03 meters per second. At what rate is the radius of the pile changing when the diameter is 26 meters? The volume of a right circular cone is V equals pi over 3 r squared h. So that's a lot of information kind of given to us all at once here. When you have all of this information and you get that feeling like, I don't know where to begin, start with basic things and work yourself into more complex ideas. A great place to always begin word problems is drawing some sort of diagram that'll help you start recognizing where pieces of information would go. So for instance, here we have wood mulch removed from a train car. So I'll put the train car right here, and it's going onto a conveyor. So let's just say this is my conveyor belt. Then it is dropped onto a conical pile of mulch for further processing. So a conical pile is just going to be shaped like a cone. So I'll draw the best cone I can there. All right. And it's pretty basic drawing here, but it has all the elements that we need. So let's start looking at the information that's given to us. All right, so the mulch is falling from the conveyor at a constant rate of 7.5 cubic meters per minute. So these little dots right here, which represent mulch coming off the conveyor, that's falling at a rate, which means it's a derivative, 7.5 cubic meters per minute. And the clues here, first off, that it's a rate. Second, that it is cubic meters, which is a volume. So this is the derivative of the volume with respect to time. And I know it's a derivative because it's a rate of change. And the cubic meters tells me its volume. So dV dt is 7.5 cubic meters per minute. So cubic meters per minute. Okay. So we're getting somewhere. We're getting to put some things on the diagram that make sense. All right, so if the height of the pile is 4 meters, okay, so the height's going to base from the center of the pile. So this height is 4 meters and is changing at a rate of 0.03 meters per second. Okay, so the changing rate is now a derivative of height. So we can say dH dt, so the change in the height over time, is 0.03 meters per second. And that should have been meters per minute, just to keep everything the same unit time. So let's just make that change, because otherwise we would have to make that into meters per minute by, factors of 60, whatnot. Anyhow, so let's just leave it minute. Now, the question here, at what rate is the radius of the pile changing? So what rate is the radius of the pile changing? So that's going to be dr dt, so the rate of the radius changing. We want to know what that is, so what is that? I'll just say equals a question mark because we want to know what it is. When the diameter is 26 meters. Okay, well, let's put some more stuff on our page here. All right, so radius, for instance, the radius is going to be this distance from here to the outer edge of the bottom of the cone. So that's going to be my radius. The diameter is twice that. So the diameter is this, which goes from one side of the conical pile to the other. It's easier to measure a diameter than it is to measure a radius. But if you get a diameter, you can always figure out the radius by dividing by 2. So the diameter is just 2 times the radius. So instead of calling this diameter 26 meters, let's just interpret this as a radius that is 13, because double 13 is 26. All right, so when the radius is equal to 13. Okay, now this formula that's given right here relates volume, radius of the pile, height of the pile all together. This is what we're going to do to come up with a related rates formula. This, again, relates the variables themselves. We need something that relates the derivatives of the variables, so the related rates formula. Let's work on that. So a related rates formula we have v equals pi over 3 r squared h. All right, to make that a related rates formula, we need to differentiate both sides of this with respect to t. And in doing so, we're going to use, again, implicit differentiation with respect to a third variable. And that third variable is t for time in this case. Okay, so the derivative of v is just 1, but the chain rule with implicit differentiation tells us to take that and multiply it by dv dt. And on the other side, we have to be really careful here because we have pi over 3, which is a constant. That's no problem. We just pull it out of the derivative for a moment. R squared and h are both going to change with respect to time. So we have two variables that are multiplied together, changing with respect to this third variable. So this is going to need the product rule in order to come up with the derivative. So we have pi over 3 times the derivative of the first, and the first function I'm going to use r squared. So the derivative of r squared is 2r, but then we also have to multiply that by dr dt times the second. Okay, so that's 2 times, or the derivative of the first times the second. Now we need to do the first, which is r squared, times the derivative of the second, which would be the derivative of h is just 1 times dh dt. So as I mentioned in earlier examples, when we're doing related rates, we need at least 2 derivatives in our equation to relate 2 rates together. If you have 3 or more, that's okay. It's still related rates. You have to have at least 2. So this is fine. Now, what we can do here is potentially clean things up a bit and say this is dv dt equals 2 pi over 3 r, oops, I have an h in there as well, rh dr dt plus pi r squared over 3 times dh dt. So there's our formula. And it looks intimidating, but I think we have all the right given information in order to solve our problem with this formula. Let me just recopy it up above, and then I will be able to plug information into it easier without scrolling up and down over and over again. Okay, there we are. Now, what I'm trying to solve for is dr dt. So everything else in this equation I should be able to plug something in for except the dr dt. And once I get that by itself, I'll be able to use the calculator to help me get an answer. So starting with dv dt, we were given originally that the volume is changing 7.5 cubic meters per minute. So we'll put 7.5 in there. Then I have 2 pi over 3 times the radius, and we want to know how the radius is changing when the radius is 13. So 13 meters, I assume. We'll put in 13 there. The height of the pile is 4 meters currently, so I'll put in a 4 right there. And dr dt we will wait on because that is right now unknown. That's what we want to solve for. Then we have pi r squared divided by 3. So this is going to be pi times 13 squared divided by 3, then times dh dt, and we were told that the height changes 0.03 meters per minute. So times 0.03. Now, I don't think it makes a lot of sense to try and get an exact answer here because there are so many decimals involved. So what I'm going to do is get approximations and come up with an answer that way. So let me pull up the calculator. Okay, and what I'm going to do then is start calculating. Let's begin with the term pi over 3 times 13 squared. And right now this is all multiplication and division, so it doesn't really matter what order I do it in. Then times 0.03. So I've got 5.309. I'll just use 3 decimal places for right now. So 7.5 equals, actually, you know what? Let me just go ahead and get a decimal here too. So this would be 2 pi over 3 times 13 times 4. So this is 108.909 dr dt plus this decimal came out to 5.309. Now what I need to do then is subtract 5.309 from both sides. So 7.5 over, oops, not over, minus 5.309 gives me 2.191. Let me move it over just a bit. There we go. So 2.191 equals 108.909 dr dt. And then what that means is dr dt is going to be found by dividing each side by the 108.909. So if I take this and divide by 108.909, I get 0.020, and I'll just make that 0.02. Alright, so then dr dt is 0.02. The radius is going to be measured in meters, so it's meters per unit time, which we called minutes here. So 0.02 meters per minute.